So in the next subsection, we look at the Knuth-Morris-Pratt algorithm, which will be the final answer to how to reduce the space from the string matching automaton that we've seen in the previous section. The main innovation here will be that we don't really go using a DFA as we've done it so far, because that inevitably needs storing all these transitions. So we need a table that has the states and the alphabet symbols. We try to get away from that. The key insight here is, if you remember how we constructed this DFA, there was this state X, which is the last state we reached with the pattern where we chopped off the first symbol. And then the next step was always copying things in this table or simulating the automaton for one step from this state X. How about we do this last simulation during the matching phase as opposed to computing it up front? It's a little unclear how to formulate this nicely in automaton language, but it's possible. And the way to go is what people have called failure links. This is not how the idea originally was explained, but I think it's the most intuitive way to think about it. So we have our automaton as before, and every state now has just two outgoing arcs. One that goes with the matching character to the next higher state, and one other edge, which is a failure link. And these failure links marked with this cross, they are to take if you cannot follow the match link. But they don't consume a character. So you just follow that link and you still try to match the same character in the text. That's the key innovation, and that's what you can do with these automata that wasn't possible with the DFA. That gives them just enough flexibility to allow the smaller space. You occasionally have to follow several failure links. If you're in state 5, you couldn't match a C because the next character was an A. Then you would have to jump to 3, and you can still match the B. So you have to follow another one, still can't match the B, so you have to follow another one. That can take some time. So you have to follow several of those in a row because they don't consume a character. But we'll see how this works. Let's go through a full example briefly, just so that this idea is clear. And we start in state 0, then we read an A. So after that, we go into state 1. In state 1, we can read a B and go to state 2. And then read an A, go to state 3. So far, everything fine. Read a B, go to state 4. Read an A, go to state 5. And at this stage, we can't read the next character, which is a B. And the match transition would be a C. So we can't go there. Instead, we go to state 3 back and try again. Now, in this case, we can read a B. So that's it for that point. And we move to state 4. In 4, we can actually read the A. But then comes an A and not a C. So again, we can't follow the match link. Instead, we jump back to 3. And then try again. But 3 also doesn't accept an A. So we have to follow another failure link back to 1. And from 1, we can still not read the A. So we follow another failure link back to 0. And only in 0 we can finally read every character, because either it goes to the match link or it stays there. And then it's consumed and gone. But in this case, A actually leads us to 1. So we can move this forward. And well, a few more. So we go to this, and 4. And that's the end of the examples. I changed the text a bit here, if you remember from last time. Another way to draw this is if you remember we had guesses and checks for these algorithms. So initially we tried to find the pattern starting at the initial position. And we could get till the 5th character, but then there was a mismatch. And so this mismatch meant we go back to state 3, which means now we have 3 letters of the pattern that are still in alignment with the text. and we try to go from there. So that's the same as shifting this guess by a few positions forward, so that instead of 5, we now have only 3 overlapping with the text. So we moved it forward by 2. And we don't need to check these 3 matches. We know that they are matches. That's encoded in the automaton. And then in this case, we could go forward. And this was the case where we had to go several steps back before we could match it again. And so only the last one determines how long you really shift the pattern. Is it clear how the automaton works through the text? Try to match the next character. If it doesn't work, follow the failure link and keep that character. All right, let's do a quick wake up and test if you're following along. This is again one you have to read carefully. See how high we can get the number today. Can we get up to 30? Woohoo! We made it. You made it, guys. All right. Most people seem done. 3, 2, 1, and locked. And so we have a variety of opinions. The right one is this one. Most of you, or the largest bar at least. And so, I mean, this one. We could go up to m steps, the length of the pattern, in a completely degenerate case. So, for example, if the pattern, often in these string matching, hello, pen doesn't want. Okay, if I write with the mouse, this will look a little less nice. If the pattern consists of m occurrences of A, I wonder if I could charge this or if that's the problem. If the pattern is just MAs in a row, then the failure link automaton will always just go 1 step back. And so if you're in the last step and read a B, or try to read a B, so you're in state Q-1, M-1, you try to read a B, but there is no B, so you go back to the previous state, Q-2. You try to read a B, but there is none, so it propagates all the way through to the beginning. All right, if we encode what we've done in the automaton in pseudocode, it looks like this. It is exactly what the example showed you on the automaton, just spelled out with variables. There's a step where we compute the failure links. So remember, the automaton now is actually really simple. The only variable thing is the failure links. The match edges are always just using the next character in the pattern. And the only other thing we needed to know is for each state, where does the failure link go to? And so we can use a single array fail that tells me for state Q, the failure link goes to fail of Q. That's all that we need. Try to rescue this pen because it's a little convenient to write on the slide. Now we have 2 variables here. Once we computed the failure links, one is encoding the guess, which position in the text is the one we're looking at. That didn't really work. So it's not the battery. Okay, we'll have to do without. One is the current position in the text, and the other is the current state in the automaton, Q. And so while we're not done in the text, we try to match the next character. And if that matches, we move with the match link that makes the state one bigger, and we move one forward in the text. So that's the position in the text that we currently consider. It's not really the guess. It's moving alongside with the position in the pattern. If we reach by that the accepting state, then we found a match, and we return where it started, which is Q positions or M positions before. If we couldn't match, then we have to follow a failure link. And here we do this by following the failure link, except in the state 0. When we're in state 0, then there's no failure link really for that one. It just stays where it is. And if we're in state 0, then we consume a character. Right? So at some point, if we can't match the character at all, we have to move forward. So state 0 is a little bit exceptional here, which you can also see in the picture. State 0 doesn't have a failure link. All right, so that's the code for the Knuth-Morris-Pratt algorithm. The only thing that is missing is how to compute the failure links. We'll come to that in a second. What I want to look at first is how good is this algorithm? How fast is it? Because one thing we noticed, and I asked you in the Slido question, it could happen that you go m steps back in the string to read one character. So if we had to do this n times for every character in the text, go m steps back in the worst case, it sounds like this is n times m, which is as bad as the brute force algorithm. But if you think about it, this can't really happen, because if you go back these m steps, you're at the beginning of the automaton in state 0, and that doesn't have a failure link. So in a way, you need to first move along, and moving along means you follow the match edge, and that was cheap. You never follow a failure link and then a match edge. So for every failure link that you follow, you needed to have a cheap operation first. More formally, you can express this like this. In each iteration, we do one of two things that make progress. We either move with I through the text, and you can only move n times with I, then you're at the end. We never make I smaller. It only ever gets one bigger. And if that doesn't happen, then we shift the pattern forward in this example picture, the red part. Or in other ways, we move back in the automaton, but that kind of moves us forward too, just not in I, but in the imaginary position of the guess. And it's important for that the failure link always goes strictly one step back at least. So it's strictly less than j for every state. And so the first thing can only happen n times, as I already said, because we move through the text. And the second thing can also happen just n times, because we can't move the pattern position, the guess, more than n times. So in the worst case, both of these happen n times at most. And so the total cost is 2 times n. Even though every individual step might cost m. But as I said, this only can happen if there were many cheap steps to compensate for it. So what's missing is how to compute the failure links. And that's also important because it's part of the running time for the entire algorithm. If you remember the construction for the DFA, which I realized was Monday, but maybe you still remember, we had this state x that was kept, which was simulating the partially built automaton on the pattern where you leave out the first character. And then whenever we added the next match link, we also updated where x would go. And it turns out that X is exactly where the failure link should go. Go through the examples again if this doesn't appear so clear. If you look it up on an example, it becomes really obvious. And so a way to compute it is by simulating the construction that you've seen in the video. And in code, you do it like this. You start with, well, fail 0 is just to initialize. It's not a real failure link. And initially, we start with x in 0. Then we go through all the positions in the pattern. And the first thing is we set the failure link for the state j, which is the previous x, the previous state that you got to if you chop off the first character. And then we update where x should go next. And if we're in state x and we can match the next character, so pj is the character we want to add to the prefix of the pattern. And if that matches from x, then we can take that link. So we just increment x. That means follow a match edge. If that doesn't work, then either we reach the beginning, and so x should just stay where it is. And this -1 is just compensated by the +1 over here. So it becomes 0 again for the next iteration. And if we're not at the state 0, then we follow one of the failure links that we've computed before. So in a sense, this is again simulating the automaton on itself, on the prefix that we've already computed. And let's also analyze this. This outer for loop can only run m times, because j is never touched inside. But we have this inner while loop, which again follows failure links. So in each individual iteration of the outer loop, the inner loop could run m times. That sounds like it could be m squared. But the same trick as before applies. Whenever x is incremented, that's one iteration of the outer loop. Then that's why I wrote the code like with the -1 in here to make that in the analysis a bit easier or clearer. We only increment x in this outer loop, so it's only incremented m times in total. Whereas every iteration of the while loop, where we continue, it makes x smaller. This makes it smaller because remember, the failure link always goes strictly to the left. And this also makes it smaller. So we only have m iterations of the inner loop summed over all the iterations of the outer loop. So it's again m plus m. And it's no coincidence that we have essentially the same result in both cases, this factor 2. You will see in the tutorials that the two algorithms, simulating the algorithm and computing the algorithm, they're really kind of the same. They're written in a slightly different form, but if you show how they work on an example, that's what you'll do in the tutorials. They're computing the same steps in a sense. And with these two things together, that's the Knuth-Morris-Pratt algorithm in its full glory. We've even gone through the analysis to show that we never have more than 2 n plus m character comparisons in the whole process. And that seems essentially best possible, because at least in the worst case, we have to read the entire text and the entire pattern to find if the text contains the pattern. If there was some algorithm that somehow avoids this, you could sneakily modify the input and smuggle in an occurrence that the algorithm then wouldn't find. And so that can't be possible. So for worst case, KMP is best possible, at least up to this constant factor of 2. And also the space is decent, because we now have only a dependency on the pattern. And there's no factor sigma anymore, no influence of the alphabet size. So it's asymptotically optimal in terms of the total time and reasonably efficient in terms of the space. So that's, on that side, the end of the story. Let's briefly see how much you kept and how much you digested from this. while I was talking. So it's a long question. I'll leave you some time. It's basically about what is good about the algorithm. Twelve. Ah, okay. Pen works again. That's good. All right. I think you had plenty time for this one now. Sorry for me messing around. Let me lock this. So we have votes for many of the options. We can briefly discuss. I think it's mostly these that are correct. Okay, that doesn't fit on the screen anyways. So this one. So we compare KMP to the previous one, matching with the string matching automaton. The pre-processing is faster because you don't have the dependency on sigma. This might not be in all cases faster, but it usually is if sigma is not really small. And it also uses less space for the same reason. The matching is usually faster actually with the automaton because you just have one table lookup. So that's usually the fastest you can get actually. Same character comparisons, likely the other one's faster if the text is long for the same reason. We have this factor of 2 in KMP, which is not nothing. But yeah, I stress this part often enough. And so we like to have something that doesn't depend on the alphabet size. Goody. One last thing on KMP. This failure functions, the failure links that we computed for the KMP algorithm, they turn out to be quite versatile and useful in other contexts. And so people have reinvented this a few times with different notation. So there's a thing called the KMP prefix function, which is essentially our fail, but shifts the index by 1. And there's an alternative definition for fail or for f. And I think that's something is worth memorizing, is worth for you to keep in mind. And there's a picture that goes along it. If this is our pattern, then we look up to a certain point j, so maybe I should put j slightly to the left because it's to the right because it's excluded. So the jth character is excluded. We look at the prefix of the pattern of length j. And then fail j is the length of the longest prefix of this that I can align with my, seriously, now it's off again. Oh gosh. So it's the longest prefix. We want the shortest shift here, or the longest overlap. So this should be the maximal length overlap. Well, this is again the pattern, just shifted a bit. Shifted a bit, at least one position, and all these positions here in between, they match, so they are the same. Okay? So you take a string, you ignore a part at the end, you'd only look at a prefix, and you ask how much can I take this prefix and shift it forward and it still matches. You want to have the maximal overlap. And then fail j is the length of this overlap. Well, no, not quite. It's the length of the well, that's the same, yeah. It's the length of this prefix, the length of the green part. That's our fail j. All right. This will come haunt us again in the next unit.